A vector, whoa, that was intelligent, is a quantity. Yep, I did.
Yeah.
Okay, so it's an arrow, okay, basically. But what we have is a direction and a magnitude. Okay, that is the interpretation of the length of a vector. Okay. So the magnitude is size. Okay. Now that can represent speed or velocity. We can use it to represent acceleration. We can do a whole bunch of neat stuff with it. Have you ever seen on the news, you know, they'll have a big picture up there, a map of the U.S., and they'll have a bunch of little arrows on it. Some of them will be longer and some of them will be shorter. Okay, they use that as a wind direction, but they're vectors, so the longer the vector, the higher the wind speed, right? And then the direction and the magnitude. So there's one way that it is used. That would be an application of Green's theorem, vector fields. When you get into Calc 3, you start really working with different interpretations of what these look like. It's kind of like a slope field with vectors. Okay. But for now, we're just going to keep it simple and put a vector into everything that you already know for the next couple days. Okay. So a vector, notice the parametric format, right? So a parametric was x of t, y of t. To represent a vector, all we do is add brackets on it instead of little arrow brackets instead of the parametric has coordinate brackets. Okay. So there's the difference between a vector and a parametric. We pretty much will work with them the same way.
The difference is just the brackets?
Yeah, so a parametric gives you a point, right?
Sure.
A location
I didn't even notice that at first, but
at a time. A vector gives you a location, direction, and a magnitude at a time.
And that's dictated by the weird bracket instead of this parentheses?
Yep. Okay, most of the math is the same. But the nice thing about vectors is that you can derive the vector, position vector, and you get velocity, and derive to get acceleration. It's that same relationship that we've studied. Right? And then same formulas as parametrics for speed and length of arc. Okay, you're just putting it in, it's just a vector. All the calculations are all the same. You have nothing more to memorize. You just have to remember the difference between the brackets and the parentheses and what it does for you. This is a lot more useful. Again, and then derivatives. Okay, dy dx. You still have dy dt over dx dt. Okay, as the derivatives. So we'll get into calculating a second derivative. It's a little more involved, but it's still the same thing as a parametric. All right. So I'm just going to give you a couple examples today and let you work. Okay. So example 1. A particle moves in the xy planes at any time t. The position of the particle is given by x of t and y of t. So the position vector is that right there, correct? Mm-hmm. What's the velocity vector when t is 1?
3t squared plus 8t, comma 4t cubed minus 2t squared.
Okay, so habits die hard. That's the velocity vector. Now at time 1, what do you do at the time? Plug it in. So we have 3 plus 8 is 11, and 4 minus 3 is 1. Yay! Right?
And then when we plug those into the...
You're done.
What?
Find the velocity vector when time is 1. That's it. What were you going to do with it?
We plug them into the velocity equation.
Don't need to, because they don't ask
Because it
for
doesn't ask for
the
the
velocity.
velocity,
It asks
okay.
for the velocity vector. Okay.
If you were to get to that point and then go on the test, would they dock you?
No, but it's a waste of time.
Just do it.
You're docking yourself, really. Okay. Acceleration vector when time is 2.
Right.
Yay!
6t plus 8 comma 12t squared minus 60.
And
14. 20.
T is 2.
Oh,
Pay attention.
$36.
So, okay. So, pretty straightforward, right?
So are these ones where as long as you have no variable, it's fine, so you just leave it as 6, 3 plus 8.
You could. Yeah. You could. Okay, all right. Okay, example 2. The particle moves in the xy plane so at any time t, with t greater than or equal to 0, the position of the particle is given by x of t and y of t. Find the magnitude of the velocity vector when t is 1. Okay, so again, you reference your formulas here. Magnitude of the velocity vector right? So it is the parametric speed equation, correct?
Mm-hmm.
Okay, so we have square root of dx dt squared plus dy dt squared. Does that look familiar?
Yeah.
In pre-calculus, that would be the distance formula.
Ah, I think that was actually
Because,
bio.
so if you look at my original, vector, correct? This is 0, 0.
Mm-hmm.
Doesn't matter in the distance formula, right? So if you go to this one, you have 0, 0, and then all you're worried about is the slope of the function using the Pythagorean theorem. That's what you're doing. Okay, the change in x and the change in y squared, square root it. You got a distance formula here, Pythagorean theorem. Okay, so.
Oh, that's weird. Yeah, it all comes together.
Right? Yeah, see how that is so,
They did a
so
little
pretty.
switch.
I had a former student spam me on Facebook, so I just said, call me, and he called me. That was Monday night. And we had to go through all this. Like, why do you like math? I'm like, it's just so beautiful and it's so elegant. Everything connects, and this is an illustration of that. Now through vectors and calculus and geometry and pre-calculus, all just comes together in a nice neat package.
So wouldn't that be, how is that magnitude then? Because magnitude
Well,
is the
let me draw it out. Magnitude is length.
Oh, I was thinking of it as a displacement.
Same thing.
Yeah.
Yeah, you're just not, displacement is a location description.
Yeah.
Magnitude is a distance description,
Okay.
right? So, yeah, so x, y, if you wanted to find the length of that, you have the Pythagorean theorem right there. Right. Or the distance formula with 0, 0.
That's weird. Now
Is it
think
kind
of
of
like
like
triangles as equations.
Like we're just finding the intersection points of two equations that just happen to connect two triangles.
Is that right?
Yes.
Derivatives, and then at 1,
25 plus 9.
dx dt at time 1, 5, dy dt.
-3.
So we have the square root of 35 squared plus 33 squared. 25 plus 9 is the square root of 34.
And that's the answer?
That's it.
Cool.
So,
My favorite
By
part
the
about
formula.
calculus.
what?
My favorite part about being in calc is like root 34.
Done. Yeah. Now, if you were in a real world context in physics, you might say 5.994 feet per second. You'd have to finish it, but as a mathematical problem, it's difficult. Okay. All right.
That's the number you put under the computer.
Yeah, that.
Okay, last one, and then you get to work the rest of the hour. Example 3. The particle moves in the xy plane so that x is root 3 minus 4 cosine t, and y is 1 minus 2 sine t. 0 to 2 pi.
Ooh. So we're just writing the equation, we're not evaluating?
The path of the particle intersects the x-axis y. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Do not evaluate.
So that should be plugged into
So
the
we
equation?
find the x-intercepts,
Mhm.
right?
Right.
How do we calculate this?
Use up the root
Is that equal to 0?
No, x-intercepts.
Oh, so
Oh,
set A equal to 0?
What?
Oh, no.
It's backward. I'm gonna write you up for that.
That's where y is 0.
Yes, if you have a intersection, that means y is 0. So set the y equal to 0. Right? Now you have a trig problem. We did this exact problem in pre-calc the other day. Not the other day, like the other month.
Me too.
So 1/2 is sine t, right?
I mean, it's not wrong to say the other day if it's
Technically,
Well, the other day I probably wasn't here.
one of the other days that exists within time.
That narrows it down.
The phrase the other day is ambiguous. It could mean just about anything.
It implies recently.
So that'd be 1/2 divided by sine or arc half sine?
So, yeah, sine inverse of a half. So where is sine 1/2 is what you're asking, right? In radians.
Is there,
Is,
Is that arc sine or?
Yeah, arc sine, sine inverse.
This one.
it's 30 degrees.
Yep, which is in radians.
30 over 180, pi over 6.
Okay? And,
Oh,
because it says there are two, if there's one over here.
From 0 to 2 pi, it's
The other
reverse,
side
which
is
is 2 pi over 6? No, not 2 pi.
it's 30, 150.
150, so,
150 over 180. Someone want to do that?
Pi over 6?
it's 6 pi over 6 minus pi over 6. So 5 pi over 6, that's how I do it.
Oh,
The 6
my
pi over 6
goodness,
is
that's
pi
so much easier.
minus pi over 6. Okay.
Wow.
All right, distance traveled. So we have our two x-intercepts, our times.
Integral,
What's our distance traveled formula?
the integral of our length.
Yeah, so there you go. So integral from,
6 minus pi over
It
0.
would be 0 to 2 pi, wouldn't it?
No, it's between the two.
between the two x-intercepts. And then we have the square root of, oh, what's the derivative of that?
I don't want to find that out.
3, 1/2. 3 halves.
The root of cosine, negative sine, right?
Yeah, negative sine, so.
4 sine
That's a
t
constant. Wow.
squared.
It's like,
Derivative of that.
What are you trying to do?
Three you go. We have to solve it.
You have
Could
to
do
plug
that
in
anyway.
as do not.
What does the problem say?
Do not evaluate.
What? Write an expression that
That's it,
represents
you're
your
done.
distance traveled.
A lot of, again, a lot of parametric, vector, polar, the problems are really nasty, so they're just asking you to write the formula. Okay, surface area, all those big formulas that we're learning now, the last month of BC, it's all probably gonna be like a, is this the right formula question?
It all comes to a full circle.
Yep.
No.
All right, so there's your day one homework.
Best of my
I
luck.
don't know how many problems. 12, 13, there are a lot of problems, so take your time. I give you over a half an hour and use it wisely.
Thank you.
I'm going to sit down, because my thumb is.
So just stay